We are Group 10 and we are going to present the design and CFD simulation of a stirred tank. Agitation and mixing of fluids are some of the most used unit operations in process design. These operations occur in agitation systems that include a source of agitation. These systems can be made up of liquid-solid or liquid-gas phases. The source of agitation transmits energy to the fluid by mechanical means to acquire movement inside a vessel. Therefore, the design of the agitation tool, known as the agitator or impeller, is the most important factor in defining the hydrodynamics of the agitation system.
To analyze transport phenomena and the behavior of the fluid in the geometry, two meshes were developed on StarCDM Plus software. One of them is polyhedral mesh that allows to have a larger number of cells, substantial amount of information about neighboring cells and their environment, and therefore it increases the accuracy of calculation. The second one is layer mesh that allows to have values information in critic zones, like zones near to the wall where the no-slip condition is valid, and to capture the hydrodynamic boundary layer appropriately. In addition to determining the most favorable number and size of the cells, a mesh-independent test or MIT was developed, having the base size as a criterion of selection because it has the major incidence above the calculation. In this case, it was compared the number of the cells, the CPU time, and the power number. One of the mesh evaluated was the quartz mesh, which has the smallest number of the cells and the highest base size, as shown in the figure. The next one was the normal mesh, which has the medium base size and the medium number of the cells. As shown in the figure, the cells was smaller than the quartz mesh. Finally, the last mesh was fine mesh, which has the smallest base size as shown in the figure and the highest number of the cells. In order to select the best mesh to use in the simulation in CFD, the results of MIT were evaluated. As shown in the figure, by a higher number of cells, the CPU time increases. But if we compare the result of the power number between normal and fine mesh, the results were very similar. But exists a significant difference between quartz and normal mesh. Therefore, in order to reduce the computer expense and the difference between results, the normal mesh was selected.
In order to determine whether the simulation and mesh conditions are appropriate or not to a stirred tank, and to compare two different impeller geometries, a Rushton and a pump impeller were used to run 6 different simulations with low, transition, and turbulent flows, and different reports were analyzed. The first of them was the power number as a function of Reynolds. It can be seen that CFD results are partially apart from the literature, presenting a root mean square of 1.41, which is good since it is a low number. The main difference is presented on the laminar region, and this can be due because of the turbulence model that was chosen for the simulations, in this case K epsilon or Y plus treatment model. Therefore, to get more precise on the results, the model for the laminar region should be changed for a different model such as AKN low Reynolds.
The simulated power input has a similar behavior than the literature one, calculated with the theoretical power number for the stirred tank with a Rushton impeller. The root mean square error is in this case 4.53, a relatively small value that can be explained due to the laminar flow in the same way that the power number error discussed before.
These results show that the Y plus values for the laminar and transient regime are in a range less than 5, what is desired. However, for a turbulent regime, These values are greater than 5, although only in a few areas for the impeller. As can be seen in this scalar velocity result for Rushton impeller, the behavior of the fluid velocity depends on the type of regime of this fluid. Since in laminar regime the velocity is very low, while in turbulent regime the velocity is very high. Also, the highest velocity occurs at the tip of the impeller for the three types of regimes. In the result of velocity vector for the Rushton impeller, it can be observed that in the laminar and transition regime, the velocity profile does not develop completely, and therefore it is not possible to observe a clear flow pattern. However, in the case of the turbulent regime, a radial flow pattern can be observed, as the velocity vector shows that the impeller blades pushed the fluid toward the walls. We then collide with the impeller and was directed horizontally and in opposite direction to the center of the tanks, a typical behavior in radial fluids.
For the stationary state in the Russian impeller, the direction of the flow is radial, because as is shown, the streamlines move in a radial direction. This means towards the wall, impacting with it and moving upward and downward. In this animation, we can see that the velocity of the streamlines are higher than the ones obtained in the pump impeller, that will be shown later, also obtaining a higher maximum velocity. Additionally, as the velocity is higher and the flow has a very turbulent behavior, we can say that the fluid present in the agitator will be moving in all directions and giving as a result a very good mixture.
Apart from the Rushton simulation, it was decided to simulate the behavior of a pump impeller into the stirring tank. Here the results are shown, and a potential regression was done to obtain an equation that can predict the behavior of the power number at different numbers of Reynolds.
These results show that the values of the Wolge plus for the three types of regime are in a range less than 5, which is what is desired. In this scalar velocity result for the pump impeller, the same behavior can be observed as the Rushton impeller, although with lower velocities.
For the stationary state with the pump impeller, it is shown a radar characteristic, because, as we can see, the streamlines flow in the same direction as the impeller, till it impacts the wall. Also, the color bar at the left shows the magnitude of the velocity of the streamlines. In the majority, these ones are blue. This color has a very low value, near to 0 meters by second. On the other hand, the velocity of the impeller is very high, obtaining its highest value in the edge of the blades.
The power number is directly related to the power required for the mixing process. In addition, in turbulent regime, the transfer of mass and heat are maximized, so it either is better to select the Rushton impeller since it is constant for higher numbers of Reynolds. In this case, the comparison between Rushton impeller and pump impeller about shear stress, we know that the difference is almost zero because this parameter was calculated based on an empiric equation.
Although a greater shear rate requires a greater energy expenditure, the mixing process is favored, so the time of this process can be shorter. With this in mind, Rushton impeller shows a better behavior.
As shown in the figure, the efficiencies for both mobiles are very small. Therefore, the energy expenditure is considerable. Even so, the Rushton mobile allows to reduce this cost, even for higher number of Reynolds as shown in the figure.
As it is observed in the results of the rheological behavior of the simulation for each impeller, it can be concluded that the fluid used for the simulation was a Newtonian fluid because the shear stress has a linear behavior regarding the shear rate. This is the typical behavior of a Newtonian fluid, and it has been widely documented in literature. The result was expected as the simulated fluid was water and has a constant viscosity. If the fluid used was a high viscosity or a non-Newtonian fluid, it may cause issues. The required torque for achieving a satisfactory mixing may be very high for this type of fluids. In this order, none of the impellers used would work appropriately with this type of fluids, as they may cause a higher power consumption and an inadequate mixing in laminar flow. For this type of fluids, anchor, double helix, or screw impellers are recommended.
In the transient state, it is shown how there is movement in both impellers in the same direction. In addition, the velocity of both impellers is very similar, although in the pump impeller we can see a much more higher velocity present near the wall, but in the impeller and its surroundings, the velocity in both cases, Russian and pump, is very similar, around 5 meters per second. Moreover, we can see that the velocity acquired in this state can overpass the one in the stationary state.
To conclude, we found out that overall, the Russian mobile presented a good performance close to the literature, which validates the CFD simulations, even if we obtained a low efficiency and pumping number results. Also, that the geometry in a Rushton impeller showed a better behavior than the pump impeller itself, which leads to conclude that geometry as expected is an essential aspect to take into account when designing a steered system. Finally, in the transient state, we can see values that are higher than the ones in the stationary state. This is because the velocity can fluctuate too much. In addition, the streamlines in the Rushton impeller are much higher than the ones in the pump impeller. This demonstrates that a better mix in the Rushton impeller can be achieved as expected because it is an impeller widely used in the industry.